A century ago, the sound of the future was metal on metal in a factory line, gears turning, pistons driving, conveyor belts rattling, and machines repeating the same motion over and over again. Today, the sound of the future might be quieter, the whir of electric motors, the click of sensors, the soft balance correction of a walking humanoid robot. Between those two sounds lies one of the most fascinating stories in modern technology. This is the history of robotics, from industrial arms to humanoid machines. Before robots were real, they were imagined. Long before engineers built programmable machines, writers, inventors, and dreamers were already asking a powerful question: what happens when humans create artificial workers? Ancient myths featured mechanical servants and animated statues. Centuries later, automata, intricate mechanical devices that could move in lifelike ways, appeared in courts, workshops, and exhibitions. They were not robots in the modern sense, but they revealed something important. People were deeply fascinated by the idea of building motion, intelligence, and labor into machines. The word robot itself is relatively modern. It came into popular use in the early 20th century, drawn from a term associated with forced labor. From the beginning, that idea mattered. A robot was not just a machine. It was imagined as a machine that could work. That concept would become much more real in the industrial age. The early foundations of robotics came from several different fields at once: mechanics, electrical engineering, control systems, and manufacturing. Factories had already transformed production through mechanization, but mechanized equipment usually did one thing in one fixed way. A truly robotic system would need something more. It would need to be programmable. It would need to repeat tasks reliably. And ideally, it would do work that was dangerous, boring, or physically demanding. That breakthrough began to take shape in the mid-20th century. In the 1950s, the idea of the industrial robot moved from theory toward reality. One of the key pioneers was George Devol, who developed the concept of a programmable manipulator. He later partnered with entrepreneur Joseph Engelberger, who is often called the father of robotics. Together, they helped create one of the first industrial robot companies and push the idea that robots could become practical tools in manufacturing. This was not the age of walking androids, it was the age of the robotic arm. These early robots were built to perform repetitive tasks with precision and endurance. They did not look human because they did not need to. In a factory, what mattered was reach, strength, repeatability, and control. If a machine could lift hot metal parts, weld continuously, or move objects with exact timing, it offered enormous value. That became clear in the 1960s, when one of the first industrial robots, Unimate, was installed in a General Motors factory. Its job was simple but important: handling hot die-cast metal parts and performing repetitive tasks that were hazardous for people. It marked the beginning of something much larger. Robots were no longer science fiction. They had entered industry. From there, industrial robotics expanded steadily. Through the 1970s and 1980s, factories around the world began adopting robotic systems, especially in automotive manufacturing. Car production was especially well suited to automation because it relied on highly repetitive processes: welding, painting, assembly, and material handling. Robotic arms excelled in those environments. They could work with speed, consistency, and precision, and they did not tire over a long shift. Japan became one of the global leaders in this transformation. Japanese manufacturers embraced robotics not just as a novelty, but as a serious strategy for productivity and quality. Europe and the United States also invested heavily, and over time robotic automation became a central part of modern manufacturing. This changed more than factory floors. It changed how people thought about robots. For much of the public, a robot was still imagined as something humanoid, a machine with arms, legs, and maybe even a face. But in practice, the most successful robots were often fixed, specialized, and visually unglamorous. A robotic arm bolted to the floor did not look like the future from a movie. Yet it was transforming the economy in a very real way. And that tension has followed robotics ever since. There are really two stories in robotics. One is the story of practical machines built for useful work. The other is the story of human ambition, the desire to create machines that move, adapt, and perhaps even resemble us. Sometimes those stories overlap. Sometimes they move in very different directions. As industrial robots became more capable, researchers began pushing toward broader forms of autonomy. This is where sensors and computing started to matter even more. A machine that simply repeated a preset motion was useful, but limited. A machine that could detect its environment, adjust to variation, and make decisions within a programmed framework was something more advanced. That brought robotics into closer contact with computer science and, eventually, artificial intelligence. By the late 20th century, robotics was no longer just about heavy industry. It was expanding into laboratories, universities, hospitals, warehouses, and even homes. Mobile robots became an important frontier. Instead of being fixed in place, these machines could navigate through space. Some were built for research. Others were designed for logistics or exploration. In parallel, robotic systems began appearing in medicine, where precision was especially valuable. Surgical robotics opened up new possibilities for minimally invasive procedures, giving doctors enhanced control, stability, and visualization. At the same time, robotic exploration changed our relationship with extreme environments. On Earth, robots were sent into dangerous locations like bomb sites, deep water, and disaster zones. Beyond Earth, robotic spacecraft and planetary rovers became some of humanity's most important explorers. A robot could survive where humans could not easily go. It could work in vacuum, radiation, freezing darkness, or distant planetary terrain. In a way, robotics became an extension of the human body. A robotic arm on a production line extended industrial labor. A surgical robot extended the hand of a surgeon. A Mars rover extended human curiosity across millions of miles. Robotics was no longer one field with one purpose. It was becoming a broad technological language for action at a distance, in risky environments, and at high precision. Then came another major shift. Robots began moving into spaces designed for people. Warehouses, for example, became major proving grounds. Instead of putting a robot behind a cage on an assembly line, companies began developing systems that could move inventory, assist workers, and optimize logistics. This kind of automation often mattered less to the public imagination than humanoid robots, but it had enormous economic impact. Quietly, robots were becoming essential to the global flow of goods. Homes also became part of the robotics story. Consumer robots were usually limited compared to the machines seen in research labs, but they introduced robotics into everyday life. Robotic vacuum cleaners, lawn mowers, and educational kits showed that robots could be useful in ordinary settings, even if their intelligence and capability were narrow. And still, the dream of humanoid robots remained alive. There is a reason engineers keep returning to the humanoid form. Human environments are built for human bodies. Door handles, stairs, tools, shelves, pedals, and workstations were all designed around our shape and movement. A humanoid robot, in theory, could operate in those environments without needing the world to be redesigned around it. But theory is easier than practice. Walking on two legs is extremely difficult. Human balance is so natural to us that we barely think about it, yet it requires constant sensing, adjustment, and coordination. Grasping objects is also deceptively hard. So is moving safely around people, recognizing context, and responding flexibly in unstructured environments. Industrial robots succeeded early because factories could be tightly controlled. The real world is much messier. That is why humanoid robotics has developed in bursts of excitement, followed by periods of realism. Some of the most memorable humanoid machines emerged from research programs and demonstration platforms. Honda's Asimo became one of the best-known examples, showing that a robot could walk, climb stairs, gesture, and interact in ways that felt surprisingly human. It was a milestone, not because it replaced workers, but because it showed the public how far robotics had come. Other projects pushed in different directions. Some emphasized dynamic movement, teaching robots to run, jump, or recover balance after being pushed. Others focused on dexterous hands, expressive faces, or social interaction. Some researchers pursued humanoids for service roles, elder care, or hospitality. Others saw them as future labor machines, capable of doing physical tasks in warehouses, factories, or even homes. In recent years, progress in artificial intelligence has accelerated that conversation. A robot's body is only part of the challenge. The other part is perception and decision-making. A machine may have arms and legs, but without better vision, planning, language understanding, and environmental awareness, it remains limited. Advances in machine learning have improved object recognition, navigation, speech interaction, and adaptive control. That has made robots appear more flexible and responsive than earlier generations. Even so, robotics remains stubbornly difficult. A chatbot can generate language without worrying about gravity. A robot in the physical world has to deal with friction, weight, collision, battery limits, timing, and uncertainty. It must sense, decide, and act, and all of that has to happen reliably in real environments. This is why progress in robotics often feels slower than progress in software alone. The physical world is unforgiving. Still, the momentum is real. Today, the robotics landscape includes industrial arms that are smarter and safer than earlier generations, collaborative robots designed to work near humans, warehouse robots moving goods at scale, surgical systems assisting doctors, drones operating in airspace, quadruped robots navigating uneven terrain, and humanoid prototypes aiming to become useful general-purpose workers. That phrase, general-purpose worker, is at the center of the current moment. For decades, most robots were single-purpose machines. They were excellent at narrow tasks in controlled settings. Now, many companies are chasing something broader. Robots that can adapt across tasks, learn faster, and operate in spaces not perfectly structured for automation. If that goal is achieved, it could reshape labor in manufacturing, logistics, healthcare, construction, and domestic assistance. Humanoid robots sit right at the edge of that possibility. Supporters argue that humanoids could eventually take on repetitive, dangerous, or undesirable tasks in human-centered environments. Critics point out that the humanoid form is often inefficient, expensive, and harder to maintain than specialized machines. And both sides may be right. In some places, a robot with 2 arms and 2 legs may make sense. In others, wheels, tracks, or a fixed arm will remain far more practical. That tells us something important about the history of robotics. The field has never moved in a straight line toward one perfect machine. Instead, it has branched outward. Some robots became stronger, some became smaller, some became more precise, some became mobile, some became collaborative. Some became more human-like, while others proved that looking human was not necessary at all. What unites them is not appearance, it is purpose. Robotics has always been about transferring action to machines. Sometimes that means lifting steel in a car plant. Sometimes it means assisting in surgery. Sometimes it means exploring Mars. Sometimes it means trying to build a machine that can walk into a room, understand what needs to be done, and do it safely. And that last goal remains one of the great unfinished projects of modern engineering. We are living in an era where robotics is becoming more visible again. Not because industrial robots are new, they are not, but because the boundary between machine capability and human environment is shifting. The question is no longer just whether robots can repeat tasks. The question is whether they can adapt, collaborate, and function in a world built for us. That is what makes humanoid machines so compelling, even when they fall short. They represent a deeper ambition than automation alone. They represent the dream of embodied intelligence, machines that do not just calculate, but move through the world. From the first programmable industrial arms to the latest humanoid prototypes, the history of robotics is really the history of how humans have tried to turn intelligence into action. It began with fixed machines repeating the same motion in the same place. It has evolved into a global effort to build systems that can sense, decide, balance, learn, and work alongside us. The factory arm and the humanoid robot may look like very different inventions, but they are part of the same long story. The effort to build tools that do more than extend our strength. Tools that can, in some sense, act on our behalf. And maybe that is why robotics continues to fascinate us. Because every new robot forces us to confront the same question in a new form. Not just what machines can do, but what remains uniquely human when they begin to do more and more of what once only we could do. That's all for today.